Have you ever thought about holding a piece of a star in your hand? Well, it sounds like science fiction, but it's really happening. Today, we're going to be cosmic detectives, and we're analyzing actual dust from ancient, long-dead stars that has traveled across the galaxy to end up right here on Earth. So let's see what these tiny cosmic fingerprints can tell us.
It all boils down to this one really amazing question. You find this microscopic grain of carbon inside a meteorite, and you know for a fact it didn't come from our solar system. What secrets is it holding? Well, as it turns out, that tiny speck is like a time capsule, and it's carrying a message straight from the fiery atmosphere of a dying star.
All right, so here's the deal. We're not just looking at any old space dust. We are laser-focused on these very specific particles that were born in the atmospheres of red giant stars billions of years ago. And deep inside them, they have this really unique form of carbon, one where the atoms are all jumbled up, holding the secrets of its violent birth. These little time travelers are called pre-solar grains. Yep, because they existed before our own sun even formed. And their core is made of something called unlayered graphene. So, picture this. In the super chaotic, hot atmosphere of a dying star, carbon vapor starts to supercool into tiny little droplets. These droplets begin forming sheets of graphene, but it's not the perfect, super organized stuff we hear about. No, this stuff is, well, it's a bit of a mess. And that messiness, that's our first big clue.
So, to really get how this cosmic material was made, you can't exactly, fly a spaceship back in time to a red giant. So scientists did the next best thing. They tried to forge their own stardust right here on Earth. But that, as you can imagine, is a huge challenge. I mean, how do you even begin to replicate the inside of a star in a lab? And this is where we hit the fundamental problem. Out in a star's atmosphere, carbon vapor cools down slowly, gradually, in the massive open vacuum of space. It's a truly containerless process. But in the lab, scientists have to use what's basically a carbon oven. The second you put walls around the process, you change everything. The carbon is forced to condense and cool on a completely different, much faster timescale. And that right there is the key to this whole mystery.
And when I say faster, I mean unbelievably fast. In the lab's carbon oven, a brand new particle of carbon can form and slam into a wall in about 10 milliseconds. I mean, that's less than the blink of an eye. In space, those same particles would have had hours, days, maybe even longer, to gently cool and arrange themselves into a perfect structure with absolutely nothing to run into. That difference in cooling time, it changes everything.
Okay, so we've got two samples, one from a star, one made in the lab. We know they were created under completely different conditions. But how do you actually quantify that? How do you look inside these microscopic grains and see exactly how their environment shaped them, atom by atom? Well, that's where the real detective work kicks in.
The main forensic tool for this entire investigation is a technique called electron diffraction. It's this incredible method that lets scientists look right past the surface and read the atomic blueprint of a material. It's how we get our evidence.
The best way to think about electron powder diffraction is as an atomic fingerprint scanner. Seriously, you fire a beam of electrons at your sample, and the way those electrons bounce off and scatter creates a totally unique pattern. If the atoms are all lined up neatly and organized, you get these sharp, clear peaks in your data, a perfect fingerprint. But if the atoms are a jumbled mess, the peaks get wide and blurry, and you get more of a noisy, smudged fingerprint.
All right, so we have these atomic fingerprints, these patterns of peaks and noise. How do we turn that raw data into a hard number that tells us exactly what we're looking at?
The goal here is actually pretty simple. We want to measure something called the fraction crystalline. Or in normal English, we're trying to figure out what percentage of the atoms inside our little speck of dust stardust actually manage to line up into perfect organized graphene sheets versus the atoms that are still just a chaotic jumble.
And here's the clever way they do it. First, you take the atomic fingerprint of your real sample, the actual stardust. Next, you use a computer to generate a model of what a perfect, 100% organized version of that same material would look like. This gives you a flawless fingerprint to use as a reference. Then comes the crucial part. You compare the height and the sharpness of the peaks from your real messy sample to the peaks from the perfect computer model. That comparison lets you calculate the exact fraction of your material that's perfectly organized. It's a brilliant way to put a number on atomic level messiness. So, after all that incredible work, making stardust in a lab, scanning its atomic fingerprint, comparing it to the real thing from a meteorite, what was the final verdict? What did the evidence actually show?
The results are just wow. They're so clear, this chart shows it all. The real pre-solar stardust, the stuff that cooled slowly out in space, was about 40% crystalline. But the version made in the lab, which cooled in milliseconds, it was only about 12% crystalline. That is a massive difference. It's not even close. This is our smoking gun.
And if you dig into the details, the story gets even clearer. It wasn't just that the real Stardust was more organized overall. The actual graphene sheets inside it were about 10 times bigger, averaging over 600 atoms per sheet, compared to just 60 in the lab-made sample. You can draw a straight line. That super long, containerless cooling time in a star gives the atoms the time they need to form bigger, more perfect structures.
As the researchers themselves put it, the key is the time at temperature. Just giving those carbon atoms more time to cool down and get settled makes all the difference in the world. And understanding this helps us piece together the exact story of how elements are created in stars and then shot out across the universe to eventually form planets and, well, even us.
So, you might be wondering, okay, cool story, but why does this really matter? Well, on one level, it's fundamental astrophysics. It helps us fine-tune our models of how stars live and die. But it's also cutting-edge material science. If we can master the art of building these complex carbon structures, they could be used for incredible things, like new kinds of barriers that can control how things move on a molecular level. We're literally learning from the stars to build the technology of tomorrow.
And that really just leaves us with one final, mind-bending question. We've just seen how scientists are basically reverse engineering the recipe for Stardust. So, what's next? What other exotic materials forged in the hearts of stars or the chaos of exploding supernovas could we learn to build right here in the lab? It seems the universe is the ultimate cookbook, and we're just starting to read it.